Everyone. It's my pleasure to introduce you today to Alois Mader's model of human energy metabolism. So, what is this model and how does it work? In the 1970s and 1980s, sports and exercise in science in Germany was at its peak. And so this was led by a group around Wilder Heumann. He's here in front. He was a physician and he did amazing stuff already. In 1963, he published data on 2,800 VO2 max tests on people aged from 6 to 80 years of age, women and men, fit and unfit. And so this was a huge amount of data, and this is not really appreciated internationally. Here's Hermann Heck. Hermann is now well in his 80s, but he's ultra smart. Just published a book in 2022, which is over 600 pages on lactate. And he conceptualized the idea of the maximal lactate steady state. Then here's Richard Rost, another physician. So they're all physicians. He also did quite a few contributions, but he passed away early because of cancer. And this is Alois Mader. Alois Mader was really the most intellectual of all of them. He was born in the East, then spent some time in Halle, where he developed microsampling, and determination of lactate in tiny, tiny samples instead of milliliters of blood. And in the back of a car, he fled to Western Germany, where he joined Wilder Heumann's group. So Wilder Heumann was a super nice guy. He was a legend at the Deutsche Sporthochschule, but unfortunately, he passed away a couple of years back. So this is a group, and one problem with the Cologne Sports Medicine Group is that their work is underappreciated internationally. And so how I got involved in all of this. So all of these guys were my teachers, and I was really impressed with them. And I thought, well, everyone must know them. And I realized when I went to the UK that actually they weren't all that widely known, and they weren't as known as they deserved to be known. And then in 2021, so there was this review by Poole et al. In the Journal of Physiology entitled The Anaerobic Threshold, 50 Years of Controversy. And I was really gobsmacked that in this review they didn't mention the first publication of a lactate threshold. This was a paper by Mader et al. In 1976. It's an amazing paper that did modern lactate testing in 1976. Huge amount of data, realized actually that the power or the speed at the lactate threshold is a much better predictor of endurance capacity than the VO2 max. They even tested Eddy Merckx. So there's some amazing data in this paper. And so this wasn't cited in a paper on thresholds. Then Hermann Heck in 1985, he published a paper on the maximum lactate steady state. And while it's the first paper, the Mader 1976 paper was in German, the Heck 1985 maximal lactate steady state MLSS paper was published in English, but still it wasn't cited to my knowledge. And then also, Alois Mader developed a model which really explained how thresholds happen. And so this was also not in there. But I have to say, because Wilder Heumann, Hermann Heck, and Alois Mader, they actually didn't speak English. And as a result of that, they published quite a bit in German. And so it is understandable that they were underappreciated. And therefore, it wasn't a letter where I said, oh, you are missing the key literature on the subject. But it was a friendly letter just to highlighting that the Cologne group had made important contribution to this field. 1 year later, we went one step further and we wrote a review, Lactate Thresholds in the Simulation of Human Energy Metabolism, contribution by the Cologne Sports Medicine Group in the 1970s, 1980s. So if you're interested in their really amazing contributions to this field, then I recommend that you read that. Okay, and then in 1980s, Alois Mader shocked everyone because he said, well, I mean, we're just doing black box research, yeah? So we have a volunteer here sitting on a bike. He puts a certain workload in, he's certain glycolytic power, oxidative power, and then we measure these things, and we don't understand how these two things are linked, yeah? So if this guy is cycling or girl is cycling harder, then the lactate will go higher, the oxygen uptake will go higher. But how is it all linked? And so he aimed to come up with a mathematical model where you put this in. And then this is important. It's not just correlations that, okay, the higher the workload, the higher the VO2, so that there's some correlative modeling. But he really wanted to do mechanistic modeling. He really wanted to link one to the other so that at the end he could calculate the concentrations of ATP, ADP, AMP, phosphocreatine in the muscles, then glycolytic flux, oxidative flux, and quite a few more things. So, and he published it in 1984 first in his habilitation. So this is another thesis, which today it's not always necessary, but you get the venia legendi, and this is essentially to get a professorship, yeah, to be qualified for professorship in Germany. And he published this in German, and I just try to imagine what his examiners thought of it, because there was no one really in a position to appreciate what he had done. And also in the 1980s, he actually played around with the first computers. And in those days, you had huge floppy disks. The computers were crashing all the time. One tiny simulation took all night. And so he really, really, as a physician, he got into this big style. And he came up with a model. And no one could really judge whether this was just well, some fancy ideas which don't work or whether it was really genius. And then in 2003, there's an English version of all of this. And this is the English version. So now you're an exercise physiologist. So this is essentially everything you need to explain to link the input. So some woman or man on a cycle ergometer cycling to all these metabolic responses, to the key metabolic responses. And it's 33 equations. So I all copied and pasted them in here. And I think you will agree that you don't know what the hell is this. 33 equations. This is not what you see in typical exercise physiology. And so I think a lot of people are unsure when they had a look at the paper. I'm sure hardly anyone reads it to the end, whether Alois Mader was a madman or whether he was a genius. And I have to tell you, I think he is a genius. And let me now, for the rest of this lecture, try to make my case that Alois Mader is a genius. So here are the basics. So he starts by getting the participant data because, of course, the metabolic responses of an individual depend how glycolytic you are, how oxidative you are, what the glycogen content is your muscles. I've listed here the weight of your muscles, the weight of your body. And then this individual data combines with the workload. Yeah, so do you do low intensity work? Do you do high intensity work? And the first step you have to do if you want to model all this, you have to convert the workload into the rate of ATP hydrolysis in the exercising muscles. And then in the next step now, so this is the rate of ATP breakdown. And then you have to work, so what does it mean for the concentrations of phosphocreatine, ATP, ADP, phosphate, AMP, and so on in the working muscles? Okay, so there was an earlier paper by McGilvray and Murray, so they had done this already, so he could use these equations and modify them slightly. And then now you have to work out, because it's not only phosphocreatine, which is resynthesizing ATP. So here you break down ATP, but you have to resynthesize ATP. And it's not only phosphocreatine, but you also have glycolysis and you have oxidative phosphorylation or glycolytic ATP resynthesis and oxidative ATP resynthesis. And then he assumed that, let's start with oxidative phosphorylation or oxidative ATP resynthesis, that ADP is the key activator of this. So here's the equation, here's ADP, and it needed to be a Hill equation because he had to play around a little bit so that he figured out, so what constants do I need, what type of equation do I need, that I get realistic data of the oxygen uptake. And then in glycolysis, he assumed that ADP and AMP were the activators of glycolysis. And once glycolysis is active and you produce lactate, this is associated with the drop of the pH. And the pH is essentially a measure of the hydrogen or proton concentration, hydrogen ion or proton concentration, and this is in here. So it assumes that ADP and AMP, they activate glycolysis and that the dropping pH is inhibiting glycolysis. And then he had further equations to make sure that because lactate is produced in the muscle, it goes out into the blood. So how does this work in a human being? And I mean, he had to think of a lot of things, and essentially, bit by bit, he came up with these 33 equations. Then, well, they had a look, and to their great surprise, it seemed to really model what they were seeing in their experiments. And this is a major achievement. So let's look at some of the key equations. So this is the equation that models the activity of oxidative phosphorylation, or the VO2, because oxidative phosphorylation is also at the same time the oxygen consumption or oxygen uptake. And so here, this is an equation. It's a little bit like the Michaelis-Menten kinetics equation, but he has, I don't know, I forgot what you call it when you put something here, a number here, exponent, we say in Germany. But anyway, this is then a Hill equation, and he needed a Hill equation because otherwise he simply couldn't fit it. He didn't get any realistic data if he just assumed a Michaelis-Menten kinetic. The important take-home message is it's only one activator, which is ADP. And once the ADP goes up, then the VO2, the oxygen uptake, and the oxidative ATP resynthesis goes up. So for glycolysis, I mentioned before, it's a bit more complex. Here are some constants here, but here are the activators, ADP and AMP. So they press the accelerator once the ADP and AMP rise, and they rise during exercise. That activates glycolysis, and then once glycolysis is active and you produce lactate, this is associated with a drop of the pH, and this is modeled here. Yeah, so he didn't put pH here, but he put the hydrogen or proton concentration, and that's essentially the same thing. And then you work out the V, the velocity or rate of lactate synthesis. And this is essentially you work out the glycolytic rate. So first question, why ADP is a better regulatory molecule than ATP? Now, a lot of people, when you look at the regulation of glycolysis or so, you think sort of the key goal of metabolism is to keep the concentration of ATP constant, no matter what, no matter how quickly you change the rate of ATP hydrolysis or ATP breakdown, you need to keep the concentration of ATP constant. And this is for regulation a bit of a problem, because if ATP was a regulator, the system works so well that from rest to fatigue, this is a logarithmic scale, but even on a linear scale, the rate of ATP, sort of the concentration of ATP in the muscle hardly changes. So how do you have to read this figure now? So on the x-axis, you see the sum of ADP, AMP, and phosphate. So once you split ATP and it's not resynthesized, the concentrations of ADP, AMP, and phosphate rise. And so during exercise, ADP, AMP, and phosphate rise. This is the situation at rest. So it's little ADP, AMP, and phosphate. And at fatigue, you have comparatively high concentrations of ADP, AMP, and phosphate. So now back to the question, why ADP is a better regulatory molecule than ATP? Well, what you see here in the logarithmic depiction is that ADP is rising throughout. Yeah, the ATP concentration is constant from rest to fatigue. There's hardly any drop, but the ADP concentration increases. And that makes ADP, and also at the bottom here, AMP, a good regulator. Yeah, because once you have a little bit more energy, the more energy stress you have, if you call it energy stress, so the closer you're to fatigue, the greater the energy stress. So essentially, the further to the right you are here on the scale, the greater the energy stress. So ADP is a really good biomarker of energy stress because at rest the concentration is low and then continually increases to the fatiguing muscle. Yeah, and now if you have, for example, given a reaction that resynthesizes ATP, it just measures ADP, and once the ADP is a little bit higher, you resynthesize more ATP. And this seems to work quite well. So you play it around a little bit. If you look in the textbooks, there are many more regulators. But actually, Alois Mader tried to keep everything as simple as possible. So he used just a few regulators and saw whether this was sufficient to come up and to simulate realistic responses. And that's what he actually found. Yeah. So why is it that the ATP concentration from rest to fatigue doesn't change at all, but the ADP concentration increases a lot? Well, the reason is the ATP concentration is quite high. Let's assume ATP is, let's say, 6 millimoles. And if ATP decreases from 6 to 5.9 millimoles, or from 6,000 micromoles to 5,900 micromoles, well, then there's a big change in ADP because the ADP concentration might be just, say, at rest, it might be 100 micromoles. So if the ATP changes from 6,000 micromoles to 5,900 micromoles, that means that the ADP changes from 100 micromoles to 200 micromoles. So it doubles. Yeah. So, and this illustrates why the change from 6,000 to 5,900 micromoles in the ATP is very little. The ADP concentration, which is a result of the breakdown of the ATP, because when you break down ATP, you build ADP and inorganic phosphate. So then the ADP concentration doubles. Yeah. And so the take home message here is from rest to fatigue, the ADP concentration is continually increasing, or in other words, the harder you exercise, the higher the ADP concentration. And so this is a very good potential regulator. And so in reality, also Alois Mader found that if you just modeled everything using ADP and then also AMP, which similarly increases throughout the range, then he could come up with realistic responses of metabolism to different exercise intensities. Right. Then I've mentioned before that Alois Mader put the pH in the glycolysis equation. So glycolysis is now a system where he simplified things because there are many regulators of glycolysis, and especially the key enzyme, which is phosphofructokinase. But he just assumed that ADP and AMP were the activators and that a dropping pH is the inhibitor. So this is quite important, and this also explains if you do a 400-meter run and you go all out at the beginning. So you run the first 200 meters all out like you do a 200-meter sprint. If you've done it before, if you've overpaced, I'm sure you know what's going to happen. Essentially, your muscles, they almost stop working at the end. That's a feeling you have. And so what happens is you start hard, so the ADP concentration rises, the AMP concentration rises. So glycolysis is activated, so you resynthesize a lot of ATP by glycolysis. But then when you build the lactate, then the pH is dropping, and now the pH is inhibiting glycolysis, and glycolysis really goes down as a result of that. So here's some experimental data of a paper in Scientific Reports from 2024 that demonstrate this. So according to this data, the optimum for phosphofructokinase, which is a key rate-limiting enzyme of glycolysis, is around 8. And as soon as you go down, and that happens when you do exercise above the anaerobic threshold, the harder, the quicker the drop here. And what you see is you really, once the pH approaches 6.5, yeah, your glycolysis is really going down because you inhibit phosphofructokinase. Yeah, so this is quite important. And yeah, so okay. So now let's have a look at a different phenomenon. I mentioned that ADP is the activator of oxidative ATP resynthesis, shown here in blue, and of glycolytic ATP resynthesis, shown here in red. I also mentioned that glycolytic ATP resynthesis depends on the pH. If the pH is low, you really, really put the foot on the brake in terms of glycolysis. So, and so what is demonstrated here? These are different ADP concentrations. And this is the activity of oxidative ATP resynthesis, or equivalent or proportional to the VO2. And this is the relationship between the ADP concentration and the glycolytic pyruvate synthesis and ATP resynthesis. So what do we see? So here, if you have a lower ADP concentration, uh, oxidative ATP resynthesis is already active. And this is what we know. When you're sitting in a chair, your mitochondria already work and resynthesize ATP. And then you go a little bit harder, and oxidative ATP resynthesis increases and oxygen uptake increases because the two are, of course, coupled. And then essentially the system can max out here. So, but this is now different for glycolysis. So what you see is glycolysis only kicks in. Of course, there's always some glycolytic flux. It's a little bit misleading. If you would show here a logarithmic scale, then you would see that even at this concentration, there's some glycolytic ATP resynthesis and or pyruvate synthesis, lactate synthesis. But sort of the model works that actually only once you reach a certain concentration of ADP, then that's when glycolytic ATP resynthesis kicks in. And so it reaches this rate at a pH of 7. Of course, if you're a glycolytic athlete, the rate goes higher. So it always depends whether you're slow twitcher or fast twitcher. But at the same ADP concentration, say of 1, so you reach 90% of the maximum. I think the maximum was here calculated for pH of 7.2. But here at a pH of 7, you reach still 90% of the maximum. But if your pH is now dropped to 6.4 and you have 1 millimole of ADP, then the rate is only 30%. So you lose 60% of that. And this explains if you're overpacing yourself, if you build up a lot of lactate in the first 200 meter of a 400 meter run, then your pH drops a lot, and that essentially brings your glycolytic ATP resynthesis down, and that essentially then limits the running velocity. And what you will find is you've overpaced yourself, and at the end you have the feeling you nearly need to walk, simply because you don't resynthesize much ATP by glycolysis anymore. Okay, then, of course, thanks to the amazing work by George Brooks, yeah, the key lactate researcher in the world, he had demonstrated that lactate is not a poison, but essentially a great fuel. Lactate can convert back into pyruvate, and that can be oxidized in the mitochondria. So, Alois Mader in his model had modeled that. So, this is a 2003 equation. So, and the rate of lactate oxidation in his model depend on the lactate concentration, and it depends on the VO2. And this is also consistent with what you see in reality, because if you do active recovery, say you do a 400 meter run and your lactate is 50 millimole, it will recover quicker if you do jogging in the rest period. So the lactate goes down quicker than if you're just lying somewhere on the lawn. Yeah. So, and because if you're jogging, you oxidize more, and so the rate of lactate oxidation is a function of the VO2 that you have at the moment and of the lactate concentration. Okay, so interlude now. Well, I actually got in contact with Alois Mader because I, I did phosphorus NMR experiments, and I could actually measure some of the things that Alois Mader simulated. So initially, I was very skeptical about this model. I think it's just too complicated to model something like human energy metabolism. But when I saw that Alois Mader's model actually predicted the things I was seeing in the NMR scanner, I really, really changed my opinion and thought that Alois Mader had achieved something amazing, which is a realistic model of human energy metabolism. So these are experiments I did with Jochen Zange and Klaus Müller at the Deutsche Forschungsanstalt für Luft- und Raumfahrt, German aerospace establishment. And this was a fun time because we had a fantastic NMR magnet, but we needed to develop all the methodology. And unfortunately, we published far too little. We should have really tried harder to publish it, but there wasn't this publish or perish attitude at the time in Cologne. So people were just curious, developed it to then test astronauts and cosmonauts. So this is what we had. So this is a volunteer. Here's an NMR magnet, super ultra strong magnet. Then there is a radio frequency coil here that can send a signal into your calf muscle, and the signal comes back. And based on that signal, you can work out ATP, phosphocreatine, inorganic phosphate. And then also we had a model of exercise. So I'm really proud on this pedal here. We had a pedal. The axis of the pedal was the axis also of the foot. And then we had a strap here in order that you don't push yourself out of the pedal. And we could do isometric exercise, but even we had some lead weights because you couldn't use steel or iron because it was an ultra strong magnet. Everything would fly into the magnet and work like a cannonball. So we spent a lot of time on optimizing this, and I'm quite looking forward. We plan to do some more experiments of this now after all these years, and I'm really can't wait to get my hands back on an NMR scanner. So if you are familiar with phosphorus NMR, this is what you get. So you get a spectrum, and then you get peaks. So adenosine triphosphate, so there are three phosphates, and this machine measures molecules with phosphate in the millimolar range. And this is ATP, and you measure the three phosphates, monophosphate, diphosphate, triphosphate. Then there's phosphocreatine, which is here. Then there's inorganic phosphate, and then there's phosphomonoesters. And these are sugars in glycolysis that are bound to a phosphate. So you know in the first step, the glucose goes in, and then it gets conjugated. You attach a phosphate to it, and then all the molecules have a phosphate, and that keeps it inside the cell. And this might be data for myself because I was a volunteer. It doesn't hurt very much in this machine, just doing very hard exercise with your calf muscle. So, and this is at the end of exercise. And we really managed to get rid of almost all of the phosphocreatine. Yeah, you see, there's hardly any phosphocreatine. This is at rest, and this is here at the end of exercise. And what you see is the system works superbly in keeping the ATP concentration constant. Because you break down ATP into ADP and phosphate, what really goes up is the inorganic phosphate. And then you see also these phosphosugars in glycolysis. They are also now clearly are much higher than at rest. And this is only what you get with a fantastic scanner. We had a 4.7 Tesla scanner, and we got beautiful spectra in order to study things. And then you can quantify these peaks and actually plot them. And let me show some data. And these are data that sort of give you an insight how it works within your muscles when you do different types of exercise. So here on the x-axis, you see time. Actually, I now realize it definitely isn't seconds, it's minutes. And the gray curve here, this is a force curve. And so with these participants, this was 8 participants, we asked them to produce a maximum force. So they had to press on the pedal as hard as possible. And then we worked out 20%, 40%, and 60% of their maximal force. So they were asked to hold this force for 3 minutes, so 20% no problem. Then here's a rest period, and that there's actually some force on there because there was some tension on the system. Then 40% no problem, And then here is because you stretch the system a bit, force is a little bit lower. And then here's 60%. And then everyone started shouting like crazy because a girl or guy couldn't keep up with the force because they got fatigued. It's just a calf muscle, but simply after a couple of seconds here, with 60% of your maximal force, you fatigue, and then the force goes down, and this is the maximum force you can still produce. And then everyone is super happy once you reach the 3 minutes because then you can stop, and that's the end of the experiment. So what you see is here, this is now the ATP peaks quantified, and you see the ATP is constant. And it drops a tiny bit here when you do have this super, super fatiguing exercise where you start with a high force, but then fatigue, and then everyone is shouting at you and asks you for the last 2 minutes to keep the force you can still produce. Yeah, and then it goes back to here. So now, instead of the ATP, the phosphocreatine changes. So you see here at the beginning, this is an exercise. So you see this is 20% of the maximal force. The phosphocreatine goes down a little bit, but then reaches a steady state. And this is exercise below the lactate threshold, because what happens now is, if the phosphocreatine goes down, the ADP goes up. Presumably, the ADP is now activating oxidative phosphorylation or ATP resynthesis by oxidative phosphorylation. And this then slowly increases until it really reaches a rate of ATP hydrolysis or ATP breakdown that has increased at the onset of exercise. So the rate of ATP hydrolysis is roughly proportional here to the gray line. Yeah, so you have a quick increase in ATP hydrolysis, you break down ATP, the ATP breakdown increases for 3 minutes and then goes back to normal. Yeah, and then it recovers. Here now what you see is the ATP falls, the phosphocreatine falls much quicker, and then it recovers. And then here it really, really goes down, and so roughly when it reaches 30% of its resting value, then you can't maintain this high force, and then at the end you reach really you almost deplete your phosphocreatine in the muscle. And even though you deplete your phosphocreatine or nearly deplete your phosphocreatine, the ATP is still constant. So if you now look at the pH, so okay, 20% actually interesting and intriguing. The pH actually goes up. And so you might wonder, is this really true? This is measured data. And it is really true because what happens is the ATP is broken down into ADP and inorganic phosphate. And inorganic phosphate is a super buffer. So you have no more buffer capacity. And as a result of that, the pH transiently increases and then gets back to normal. You get an even bigger increase at the beginning of this exercise, but then you produce lactate, and associated with it, there's a drop of the pH here to a bit more than 6.8. Now you do the really hard exercise, and this is now equivalent to a 400-meter run where you start far too quick, and then essentially you have to become slower and slower and slower because you can't anymore. And so here you see a sharp rise in the pH to above 6.1. And then you produce lactate, the pH drops. And here, on average, you get a drop to roughly, I would say 6.6. I mean, some people get a drop to 6.4, really glycolytic individuals. And then here you see the recovery of the pH. Then the phosphomonoesters, you see the increase here during this exercise, but even more during this exercise. And so at the time, then also Alois Mader, he was very happy that we were doing these experiments because he realized that actually what we simulated here was pretty similar what he was predicting as a basis of his model. So moving on, some specific questions. So does Mader's model predict phenomena we know that happen in reality? The first one is the regulation of fat versus carbohydrate oxidation. So this is a classic study by Luc van Loon and Paul Greenhalgh in 2001 in the Journal of Physiology. And so they had 4 different exercise intensities, 3 different exercise intensities and rest. So here's rest. 40, 55%, and 75% of the maximum workload. Here's the energy expenditure. So at rest, maybe you have 8 kilojoules per minute. 40%, you have 50 kilojoules per minute. Then you have over 60, and you have over 80 kilojoules per minute. Then they worked out so how much was from fat oxidation and how much was from carbohydrates. Blue is carbohydrates, red is fat. And this is typical data. So actually the percentage of fat oxidation is normally quite high at rest, especially if you haven't eaten for a while. And then, but however, because at rest you're not consuming much calories, so it's only maybe 4 or 5 kilojoules per minute of fat. That increases then at 40% of the maximum workload. Now you have a bit less than 30 kilojoules, and you reach your fat max at medium intensities. In this case, I reached it at 55% of the maximal workload, and I reached a peak of a bit more than 30 kilojoules per minute. And then what happens actually, fat oxidation goes down once you go harder. And once you reach the anaerobic threshold or the lactate threshold, I know George Brooks doesn't like the term anaerobic threshold because the oxygen is not a key regulator of glycolysis. And this is also what consistent with Alois Mader's model. Oxygen isn't a key regulator in his model, but many people still call it the anaerobic threshold or the lactate threshold. Once you reach the lactate threshold, you have hardly any fat oxidation left. So the big question now, this is quite complex metabolism. It's not fully explained. Does Alois Mader's model, right from the beginning, did it actually predict such a behavior? And so let's have a look at the model. So this is what the model predicts. So one thing is a model works out glycolysis, and glycolysis results in pyruvate synthesis. And of course, now the pyruvate has two fates. It can go into the mitochondria, turn to acetyl coenzyme A, enter the TCA cycle. You consume oxygen, so all this is modeled. Or alternatively, if it's not taken up by the mitochondria, it is rising within the cell. And if the pyruvate rises, thanks to lactate dehydrogenase, the lactate rises. Okay, so this is one way to fuel the mitochondria. The second way to fuel the mitochondria is fatty acids. So now let's have a look at what Alois Mader's model predicts. So you see here two curves. The blue curve, this is actually, I think, best described as a fuel need of mitochondria. So the harder you exercise, the more fuel mitochondria need, up, of course, to the VO2 max. And so what you see is here is rest. So this is a fuel need of mitochondria. And then the red curve now, this is actually sort of pyruvate synthesis by glycolysis. So you have a tiny bit here. And what you see is, this is the amount of fuel that the mitochondria need at rest. And this is what glycolysis provides. If you eat a lot of sugar, the red curve goes higher. If you're completely carbohydrate or glycogen depleted, the curve is lower. But the glycolysis, the fuel produced by glycolysis in this, and the fuel produced by glycolysis is pyruvate, is not enough for the fuel demand by the mitochondria. So there's a gap. And simply what Alois Mader has assumed is that the difference is fatty acids, so fat oxidation. Then you reach medium intensity exercise. So here, the fuel production by glycolysis goes up. Yeah, that's a red curve. So the glycolysis produces more pyruvate. But it's still not enough because for the mitochondrial fuel need, because it went up here at 40% up here. And actually the gap has risen. Yeah. But then what happens is, once you go harder, then the ADP really reaches a point where it really, really activates glycolysis. So glycolysis kicks in. And what you see is now all of a sudden, once you come closer to the lactate threshold, which is here, now all of a sudden glycolytic pyruvate synthesis goes up. And actually it comes closer to the fuel needs by the mitochondria. And then there's a phenomenon which I have termed crossing point or maximum lactate steady state. And this is now actually a point where now glycolysis reaches or produces enough pyruvate so that the mitochondria don't need any other fuel, so they don't need any fatty acids because glycolysis produces sufficient pyruvate. So if you then push harder and increase the exercise intensity further, then actually the glycolytic pyruvate synthesis exceeds the fuel need of the mitochondria. And as a result of that, now, because the mitochondria, they don't use all the pyruvate that the cell is producing or the muscle fiber is producing, now the pyruvate is increasing over time. And as the pyruvate increases, lactate increases. And so this is actually, according to the model, the maximum lactate steady state. And what you get in this model is an explanation for two phenomena. So you find that fat oxidation in this model goes up to the maximum lactate steady state. Yeah, and it reaches the maximum. So the maximum fat oxidation is the difference between the red curve and the blue curve. And so it's biggest roughly at medium intensities. And once you go hard, actually, then glycolysis is producing so much pyruvate that the mitochondria hardly need any free fatty acids in addition to that to meet their fuel demand. Yeah, so it comes closer and closer, and then you reach a maximal lactate steady state. And so the simplified assumption in the model is that at this state, essentially, it's all carbohydrate oxidation. And once you go a little bit harder, then actually you produce excess pyruvate. So as a result of that, in the muscle fiber, the pyruvate is increasing, and as the pyruvate increases, the lactate increases. So it predicts not only the relationship between exercise intensity and fat oxidation here in this range, but it also predicts that once you reach a threshold, the mechanism is that simply now glycolytic pyruvate synthesis is above the fuel need of the mitochondria or the amount of pyruvate that the mitochondria can use. And as a result of that, the pyruvate is increasing. If the pyruvate increases, the lactate is increasing. Okay, and there's a big debate about how is fat oxidation regulated? Is it how much fat we break down into in our adipose tissue or white adipose tissue? What is it? And essentially, this is a paper by Bente Keynes in 2017. You can read it in more detail. But this is linked. Also, the ideas are linked to glycolysis-derived acetyl coenzyme I. So first you produce pyruvate and then acetyl coenzyme A. And so essentially, this is pretty similar what Mader came up with in his model to this what Lundsgaard and Bente Keynes are authors of this, what they discussed in 2017. So Mader's model potentially provides an explanation for the regulation of fat oxidation. And so this is very useful to see that even in a mathematical model, this works like it works in reality. Okay, so one thing a lot of British exercise physiologists were very fascinated with is the phenomenon of the VO2. So this is sort of some old data by Brian Whipp and Carmen Wasserman. And so what they showed is doing constant load exercise above the it's the anaerobic threshold, the VO2 does not reach a steady state but increases further. And this has been termed the slow component of the VO2. So, and this essentially is that normally you would expect that the VO2 increases during constant load exercise and reaches a steady state. But actually what people found is that it increases further. It creeps up, and people for a long time didn't have an idea why this was happening. So Mader in 1994, I think he actually said, hey, my model is simulating the slow component of the VO2. So, and because it was modeling it, so let's have a look. What does a Mader's model simulate when you do constant load intensity above the lactate threshold? So this is a lot of curves here. So let's have a look what it means. So it's constant load exercise. And this is a time axis here. It's up to 3 minutes. And so doing this constant load exercise, so one thing that's happening, you're breaking down ATP. And of course, the ATP is resynthesized, but nonetheless, the ADP concentration is increasing. Yeah, so you exercise and the ADP concentration is increasing and really goes through the roof here at the end. The second thing that happens is because the ADP is increasing, excuse me, the ADP is activating glycolytic ATP resynthesis. This is a red curve. So the ADP rises. You see there's a rise here. The ADP rises. The ADP rises and the glycolytic ATP resynthesis rises. But if the glycolytic ATP resynthesis rises, another thing is happening. So initially I mentioned, like in the experimental data, the pH is going up so that the model predicts that correctly. But then associated with a buildup of lactate, the pH is now dropping. Now you have a situation where on the one hand, you accelerate glycolysis by the rising ADP, but at the same time in the model, the pH is dropping and the pH is increasing the inhibition of phosphofructokinase and glycolysis. So essentially, there's a tug of war. So the ADP is pressing the accelerator more and more for phosphofructokinase and glycolysis, and the dropping pH is putting the foot on the brake. And now you simply need to do the mathematics to see what happens to the rate of glycolytic ATP resynthesis and pyruvate resynthesis. And this is a red curve. And so, okay, initially the pH is quite high, so glycolysis or glycolytic ATP resynthesis increases quickly. But now actually the effect of the pH on the inhibition of glycolysis is stronger than the activating effect of the ADP. And as a result of that, yeah, because the pH drops and drops, now actually glycolytic ATP resynthesis is decreasing. Okay, now there's an issue because it's constant load exercise. So that means you have a constant rate of ATP hydrolysis, unless, and I come to the unless in a minute, but you have a constant rate of ATP hydrolysis or ATP breakdown. Now, if the glycolytic ATP resynthesis decreases, I haven't shown phosphocreatine here. That's another source of ATP, another reaction for ATP resynthesis. But anyway, this is what the model predicts. The glycolytic rate of ATP resynthesis goes down. So in order to meet the needed ATP resynthesis, now the model predicts that now oxidative ATP resynthesis goes up. And now, if you now convert all these things, this is in a muscle, if you convert it to the whole body. So if now actually, so this was true, what you would expect is that the lactate wouldn't increase linearly. So if you have a constant load of a constant rate of glycolytic ATP resynthesis and lactate synthesis, you would expect that the lactate concentration rises linearly. But if you expect that you see this effect, that actually glycolytic ATP resynthesis and also it correlates with lactate synthesis, that it increases, but then the rate goes down, you would expect that initially it increases steeply and then it increases less steeply. And this is a blood lactate concentration. This is what really the model comes up with. And the model then predicts that at exercise above the lactate threshold, that your VO2 max goes here, and then you see the slow component. Yeah. And so even without assuming that there's a change of efficiency, which essentially means that over time now the ATP rate of ATP hydrolysis is increasing because you're recruiting inefficient type 2 fibers. Even if you take that out of the equation, the model predicts that if you have a constant rate of ATP hydrolysis at a constant workload doing exercise above the anaerobic threshold, it predicts the glycolytic ATP resynthesis reaches a peak early on, and then because of the dropping pH is inhibited more and more and goes down. And in order to meet the the requirement for ATP hydrolysis, now the model simply because the ADP is increasing further and ADP is activating oxidative ATP resynthesis. ATP resynthesis increases. Now, if you calculate this as a VO2, what you see is a slow component of the VO2, which Brian Wibb and Carmen Wasserman have measured in the 1980s. And actually, Alois Mader, unfortunately, in a German-speaking article in 1994, 1996, he said, look, guys, my model is simulating the slow component of the VO2 doing exercise above the anaerobic threshold. And this seems to be quite remarkable because I don't know how many people would think that you could simulate something like that with a model of human energy metabolism. So now a final thing, it seems to be considered to be a voodoo variable, the Vila max. There's lots of opinions about it. There's a lot of hype about it. Some people clearly exaggerate what it is and how good it is and how important it is. So what is a Vila max? So if you work out the rate of a reaction, you need a formula. In that formula, you normally need the maximal rate of the reaction. And Alois Mader, of course, he needed to simulate glycolysis, and he introduced a variable which he termed Vila max. That's the maximal rate of glycolysis, and you can term it maximal glycolytic ATP resynthesis, or you can also term it maximal lactate synthesis, and he termed it essentially Vila max, which is maximal lactate synthesis. So it's a maximal rate of this reaction, and you needed to calculate all of this. And then also he had a maximal rate of oxidative phosphorylation within the cell. In this model, he called it that's a maximal rate of oxidative phosphorylation, and the maximal rate of lactate oxidation, he called it the V-LAOX. So this is distracting from it. Okay, so let's have a look. And then people actually, so they did all sorts of simulation because they had a computer model of Mader's model. And then actually they realized the Vila max actually seems to be quite an important variable. So the Vila max in the model, we call it Vila max muscle because it's related to kilogram of muscle mass. And actually, sort of all these simulations, they yielded one important insight, which is if everyone is the same, if you have a higher Vila max, if you're more a glycolytic, fast-twitching athlete, even if you have the same amount of mitochondria in your muscles, but if you have a higher Vila max, and the Vila max is related to how much glycolytic enzyme you have in your muscles, then you get a leftward shift of the lactate curve. So this is simulated here. It's a simulation with Alois Mader's model by Hermann Heck. So you have a typical a graded exercise test. So here's a workload. So you increase all 3 minutes, you increase by 50 watts. And so here's a standard curve, assuming a Vila max of 1 millimole per kilogram muscle mass per second. Yeah, so you see here, so you reach 4 millimoles of lactate at 250 watts. It's not super fit. And you reach a maximal lactate concentration in this test of 30 millimoles. Now, if you now double the Vila max, the predicted effect on the lactate curve is, even if you have the same amount of mitochondria, you get a leftward shift. Now, at every exercise intensity, you have higher lactate values and you reach 4 millimoles of lactate already at a power of 200 watts. So why is that? It is simply because if you have a higher Vila max, it means if it's twice as high, it means that your muscle fibers have twice the amount of glycolytic enzyme. And so of any concentration of the activators and inhibitors, it means that you have twice the rate of glycolysis. So, and if twice as much lactate is running into your muscle, you will have higher lactate concentrations, even if everything else is the same amount of mitochondria, so capacity to oxidate lactate and so on. Conversely now, if you bring down your Vila max, so because you have less glycolytic enzymes or for some other reason, if you have it, then actually you get a rightward shift. Now you improve your power at 4 millimoles of lactate now to 275 watts. So this would be a much fitter athlete because so on. And so this is an important insight. And because naively, most people would think, well, if I have a really good endurance athlete, they have a lot of mitochondria and a very high VO2 max. And on top of that, they should have plenty of glycolysis. So when it comes to the sprint, they even outsprint everyone. But actually, sort of the simulations with the Vila Max, they suggest that this doesn't work like this, that there's actually an optimization game that you have to do. So you have to see, so what type of athlete do I need? Do I need someone who needs some glycolytic capacity, for example, given a sprinter in the Tour de France, or maybe a Nordic skier who has to really go hard up the hill and then it's sliding down the hill at low intensity? Or is it more time trialer where I really want to have super low lactate concentrations? So if you're Ironman triathlete or marathon runner, you really want to bring down your VLA max because you get this rightward shift of the lactate curve, even if you have the same amount of mitochondria and everything else is the same. But now, if you need some glycolytic component in your sport, for example, given a football player where you have intermittent sprints and so on, then actually, of course, you need plenty of mitochondria to have plenty of endurance, but you also need some glycolytic capacity. But the consequence of increasing your glycolytic capacity through training and other interventions is that you shift your lactate curve to the left. So this is an interesting insight. Actually, quite a few people have started researching this, and yeah, so is there actually any evidence that this works like this? That if you lower your VLA max, that you actually get a rightward shift of the lactate curve? Well, actually, one thing that has a similar effect than lowering the VLA max is reducing your glycogen. If you reduce the glycogen concentration, the rate of glycolysis goes down. Yeah, because I mean, the higher the glycogen up to a point, the higher it is really like the higher the glycogen concentration, the higher the VLA max. Yeah, that sort of correlates. And if you bring down your VLA max, you bring down glycolysis. There's some data on this. And this is data by George Brooks's group in 1982. And here he tests the same individuals. Ignore the upper curve. So the green curve is a typical lactate curve. Here's a work rate. And so old units, kilogram times meter divided by minutes. I don't know how this works, how this converts into watts. But what you see is a normal curve. So they reach 4 millimoles of lactate rather as a value of 1,700. Now, if you bring down your glycogen, which is equivalent to lowering your VLA max, then actually at the same exercise intensity, and obviously these individuals don't have different amounts of mitochondria because it's the same individuals. Now all of a sudden you bring down your lactate curve, and now actually you reach 4 millimoles of lactate. You would reach it now at a much higher exercise intensity of 2,200. And this is actually experimental data which indirectly demonstrates that if you do something which is equivalent to lowering the VLA max and bringing down the glycogen is equivalent to taking some glycolytic enzyme out of a muscle, leaving mitochondria and everything intact, you get a rightward shift of the lactate curve. Now, of course, this is not a good situation because you limit your substrate if you're glycogen depleted, and we all know that clearly doesn't work well. If you're glycogen depleted, you clearly have a decreased exercise intensity because you limit your amount of carbohydrate oxidation. But it demonstrates, however, that if you do something which is comparable to lowering the VLA max, you get a rightward shift of the lactate curve. And this is essentially which is predicted here in this curve. And also, okay, this is change of the VLA max. But actually now in the model, you can actually artificially do a simulation with low glycogen, and you essentially get the same behavior. So this is a very interesting variable. People have picked up on this, and now in 2025, There will be actually an online conference on the Vila Max to discuss what it is and to try to take all the hype out of the Vila Max, and to really discuss what is it. And actually, we think there are three versions of the Vila Max, and I'd like to explain that during that online conference. Yeah. Okay, and so this brings me to the end. The Vila Max certainly is an interesting variable. There's been a lot of hot air produced around it, but yeah, it's an interesting variable. There will be a conference this year organized online. Check out on Twitter X or on Blue Sky, and there will be other announcements about it. And this brings me to the end. And this is actually also showing that I'm sometimes trying to do some exercise, but I'm getting old now. And this is actually at the Costa Brava at Christmas. And this is Demi Vollering, who won the Tour de France, and she overtook me twice that day. And yeah, I feel I'm getting old. But anyway, I'm shifting now from active exercise to trying to explain exercise physiology. And I hope you got something out of it. It's all a little bit confusing, but it's just a starting point to get you interested in Mader's model. And I hope you appreciate that even if it's not totally perfect, that there's a lot of smart thinking behind it, and that it simulates, for example, given more or less, yeah, and maybe it's not quantitatively correct, the effect of exercise intensity on fat metabolism. It certainly more or less simulates that behavior. It simulates the slow component of the VO2 and has introduced the Vila max, which is the equivalent of the VO2 max. What the VO2 max is for oxidative phosphorylation, the Vila max is for glycolysis, as an interesting variable which stimulates the thinking of modern day exercise physiologists. And thank you very much for listening to me, and send me an email if you have any questions. Thank you very much.